I'm Ollie Wright, UP2070883, and this is my submission for gameplay programming called GOLDRUSH. GOLDRUSH is a 2D top-down shooter created with the Unity game engine. Billy Bob is a cowboy in Gold Rush era California. Strapped for cash, armed with a trusty firearm and a suspiciously low sense of empathy, he decides to go on a theft spree, stealing from all those who've managed to scrape together even the smallest amount of gold, mostly by shooting them in the back as they flee. The game was created over about 3 weeks in Unity, including the creation of the art assets, which were all originally created for the project. The player spawns in a world full of enemies and piles of gold, which they must collect to increase their score before they die or have won by killing all the enemies and collecting all the gold available. It features options for the creation of each level, making each playthrough unique, as well as having a main menu, a pause menu, a death screen, a win screen, and of course the main game. Enemies also dynamically react to the player using a finite state machine, making the game a lot more interesting. Going into the project, I knew it was important not to overscope, so I created a design document containing an overview of the game and the basic systems that I wanted to implement. I then spent time looking at it and boiling them down to their basic systems. These would serve as a kind of baseline for what I wanted to find within the programs that I would use to create the project. These included, but certainly weren't limited to, graphics, including sprite animation, user interface, input handling, camera movement, as well as a physics engine. From this list, I found Unity would probably be the best fit for the project. The workflow provided by the editor seemed to be the most appealing for the project with this scope, since there is a relatively simple streamlining of work within the editor. It has simple to use libraries, clear file organization, and inbuilt functions. Its selling points being the ease of use, allowing developers like me to quickly prototype and develop the games. It offers a wide range of tools, such as a visual editor, built-in physics engine, rigid body, and support for multiple platforms. This results in it being very industry relevant, with many large releases such as Overcooked, Cuphead, Subnautica, Kerbal Space Program all being made within the engine. Despite this, I did spend a considerable amount of time researching the other options, so the main competitor to Unity is probably Unreal Engine 4 or 5. But I decided against this due to the smaller scope of the game, and from my research, Unreal Engine seems to be a much more useful tool in the hands of AAA developers, essentially for teams that have the resources and time to harness the massive power offered by the engine. It offers a pretty wide range of features, including advanced graphics rendering with features like nanites in Unreal Engine 5, support for virtual reality, and real-time rendering, which is useful in the film industry, but does have applications predominantly in AAA games. However, it can be pretty challenging to learn and use, especially for developers with little experience in the engine. As a lone developer with a pretty small amount of experience in the engine, it did feel like learning it from scratch might be a bit redundant, especially considering we had studied Unity within some of the lectures. But mostly because it has so many advanced features that, in a scope this small, would probably only serve to complicate the project. Another reason that I decided to use Unity over Unreal Engine was that the workflow of a 2D game is much better catered to by the Unity engine, featuring a 2D preset as well as 2D versions of many of the methods, such as Rigid Body 2D and Raycast 2D. These allow for the simplification of both physics and raycasting in 2D, since they remove the necessity for a third dimension in calculations, making it much more intuitive for the end user, whereas similar features in Unreal Engine require a plugin called Paper 2D to compete with the much larger offerings to 2D developers in Unity. I'd also make the argument that Unity is a lot more heavily documented online, which enables for much faster workflow, being able to look up tutorials for very specific niche functions within a matter of minutes. There are multiple entire channels on YouTube dedicated just to showing very niche parts of Unity and quick 1.5 minute videos that proved really useful during the creation of my project. Also, Unreal Engine's files tend to skew a bit larger. Even though my target audience will be Windows systems, file optimization is still important if the game is intended to ship. In the same vein, collaboration in Unity is made a lot easier by its simpler source control and smaller file sizes when on source control websites. GitHub has a free plugin available, which is incredibly easy to use, or alternatively you can just use GitHub Desktop in conjunction with Unity. All it requires is a simple git ignore to be put into the files. Unreal, on the other hand, has a much more complex integration with Git, such as requiring multiple steps to set up and a much less integrated workflow. I also researched and trialed game engines such as GameMaker and Pico 8. GameMaker was ruled out because I wasn't personally a fan of the workflow. In the modular design, it felt a little daunting to me, as well as using Lua, which it was a language I definitely wasn't familiar with. From my research, I also did find it to be a little more simple than Unity, which I knew might serve to speed up the workflow a little, but personally, I knew I could handle Unity, so I decided to go with that instead. Pico 8 was ruled out because it doesn't really contain many of the features that I wanted to use, so animations and complex UI systems such as sliders for the options menu were just not applicable within the engine. Although there might be workarounds, Unity offers much easier access to these functions. Other tools used in the project were Visual Studio 2022 for the code and Sprite for the development of the art for the game. One of the main reasons Visual Studio is better than the other options is in the flexibility that it provides, supporting a wide range of programming languages, including C#, C++, and Python, that can be used to develop applications for multiple platforms including Windows, Mac, and Linux. This means developers are able to use Visual Studio to create a wide range of applications, from desktop to mobile apps to web applications. In my case, it was required for C# code within Unity, which offers inbuilt integration. From this integration, the dynamic code suggestions are incredibly useful in speeding up the workflow, while the color code highlighting and other customization makes the user experience preferable to the other options in general. The IDE includes a range of tools and features which make it a lot easier for developers to write, debug, and test code. For example, it includes an integrated debugger, code editor, and support for intelligent code refactoring. it offers a wide range of extensions that can be added to customize it for specific workflows as well, which goes for more outside of my project specifically, but it was one of the main reasons that I picked it. In relation to Unity, some of the only competitors were the original Visual Studio Code and a paid IDE called JetBrains Rider. Visual Studio Code, although faster, doesn't offer as many features alongside Unity, while JetBrains Rider is a paid program, so a developer such as myself with no budget found it just unfeasible. This was quite unfortunate because there were many positive reviews for the program. As for art, Sprite was my program of choice. It has an incredibly intuitive workflow compared to my previously used sprite editors such as Piskel, which is an online pixel editor, which requires you to download files every time you want to save since you can't save onto the website. Boasting a 99% positive review score on Steam with just shy of 10,000 reviews, it was a clear choice for the project. I used it to create and export all of my sprites and sprite sheets, which were then imported into the Unity editor. These were then used for almost every graphical element within the game, as well as the sprite animator functions that I created. Lastly, I selected GitHub as my version control method. GitHub is an incredibly useful version control tool for a Unity project since it allows developers to quickly and easily manage and track their code over time. With GitHub, devs can create multiple versions or branches of their project, allowing them to experiment with different ideas and approaches without impacting the main codebase. This makes future efforts to collaborate with other developers much easier and grants the ability to merge changes in a controlled manner. My other options for version control tools within Unity included Plastic SEM, which is the inbuilt Unity version controller, and Bitbucket. Plastic SEM is probably easier to use with the base version of Unity, since it is essentially the evolution of the deprecated Unity Collaborate version controller, but doesn't quite offer the same functionality as GitHub. It's mostly optimized for when there's a team working on a smaller project than for a single person working across multiple systems for version control. On the other hand, Bitbucket could be more useful for solo developers, as the source control is always a private repository. However, this then means it'd be much more difficult to include other developers should I decide to expand the horizons of the project and work as a team. As explained earlier, the game centers on top-down shooting mechanics with enemy AI, but the system relies on a lot of others to function. Player movement, for example, uses Unity's inbuilt input handling to take in player input and move the object accordingly around the scene. I've implemented this in a pretty simplistic way, with the limitation of my current method being that the player does move marginally faster when pressing two buttons at once to move diagonally. This is because it's adding the unit vectors of two different directions, which ends up being about 1.4 units of movement per second as opposed to 1 when going in a straight line. In order for the movement to look more natural, sprites, including both the player and enemies, were animated when walking, using a change in frame which will switch to an idle state when no input or action is being performed. In the enemy's case, this means they've reached their current target location. It uses the sprite renderer component on the relevant game objects. I selected this as it provides me with a pretty simplistic way to swap between sprites, but does limit me in terms of more detailed animation, as it requires each frame to be imported as a separate sprite and imported into a manager. If I wanted to expand the project further, I'd probably have to use the Unity animation controller, which is an inbuilt function of Unity. However, it's slightly more advanced than the sprite renderer that I used. The crosshair dynamically updates during the game, based on a raycast between the player's current position and the cursor's current position. If it's broken, the crosshair will change sprite to a grayed out version of itself. I probably could have made this more efficient if I'd used sprite renderer.color, which is a method I found later through my research, instead of swapping the sprites to a different grayed out version of itself each time. I can't think of anything more appropriate for this than raycasting as a method, since it needs to take in 2 points and calculate if there's any obstacles between them. Also, the gun uses the same mouse position to orient itself so that the barrel of the gun is always facing the crosshair. The ATAN2 function was pretty instrumental in this. This is essentially a function that calculates the angle between 2 points, and I then adjusted the gun's position accordingly. Enemy behavior is controlled using a finite state machine, which is a type of system that allows for great adaptability, and being modular allows for a lot of expansion and the ability to add more behavior types and control the switching between them. This is much easier than other equivalent systems, such as just having a long class that controls the enemy entirely, which then requires all the parameters to be met and a bunch of if statements for whenever the enemy tries to change their current state. In my specific implementation, however, I am aware that I did use a lot of public variables, and there would be much more efficient ways of doing this. So I think a solution might have been using a manager to control all the variables that I have, and also not making them public so that I can't accidentally change them from outside the class. Enemies also have a dynamic health bar which adjusts according to their health. This is implemented using a plain box sprite that shrinks its scale on the x-axis according to the proportion of the health out of the maximum health, then changing colour when their health is below a certain value. The implementation is functional but simplistic and would probably benefit from some aesthetic changes, such as an outline and potentially adding an indicator for the enemy's current state. When the enemy dies, the health bar and the script that controls the behaviour is destroyed, meaning that all is left is the sprite, which has been changed to their death sprite. When this happens, a gold bar is instantiated and then animated above their corpse, which can then be picked up by the player. From my testing, I found that people preferred the animated gold bars over the stationary ones, even though it didn't quite fit with the art style, as it just looked more appealing and more interactable. The inbuilt Unity physics engine, Rigid Body 2D, was used for the bullet mechanics and detecting collisions. This allowed me to check the tags of objects that are colliding, and massively simplifies it over the methods of doing the same thing in other engines. For example, if I wrote my game and did my graphics in OpenGL, I'd have to write an entire physics engine from scratch, which certainly wouldn't be an efficient use of time compared with the Unity. One limitation to my implementation of this is I did use the isTrigger event a lot, which means that you can't push objects around when they've been hit. So, for example, if I wanted to have an enemy get pushed back by a bullet, it doesn't quite work because the trigger event kind of negates the physics objects from colliding. I implemented a camera system that uses boundaries to adjust the camera position over the scene, rather than a completely static camera or a camera that followed the player all the time, which, from my testing with others, found to be pretty disorienting. The system works by having a central coordinate of the current camera position, then when the player reaches a bound on any axis from that, adjusting the camera position by an appropriate amount. The result of this is a box in the middle of the screen that the player is free to roam around without the camera moving before they reach the end, and it moves a gradual amount, as if they are essentially pushing the boundaries. I spent so much time implementing this system to a point that I was happy with it. In future, I would probably use systems like Cinemachine, which is an add-on for Unity, which I discovered later in my research, that may be easier. Time is used throughout the project, namely in the pause menu and within enemy AI. Essentially, the pause menu will just stop time by using the timescale command and setting it to 0, while also activating a canvas that grays out the rest of the screen and activates buttons for the menu and to resume. The enemy AI uses time in functions such as roaming, where it randomly decides to go to a position plus or minus a certain amount of its anchor point every 4 seconds, in addition to a number of other functions within the other enemy behaviors. GOLDRUSH also features a completely customizable level generation system, which takes in parameters passed by a scene manager from the options menu within the main menu. It's a randomly generated map using the size, the amount of decorative objects, amount of enemies per gold pile, amount of gold piles, and enemy spawn distance away from the gold piles that they protect. Of all of the features that I managed to implement, this was probably one of my favorites, since I feel like it adds a lot of depth to gameplay and a lot of replay value within the game. It also introduced me to static variables, as well as sliders to control values, as well as the final feature that I'm going to talk about, the scene manager. The scene manager is the master of the scenes currently being loaded, the pause menu, and carrying over the settings and variables between scenes. It contains a check for the level being devoid of enemies in gold, so that the game can end if the player is stuck in an empty wasteland. It will also load the death scene once the player has died. This manager is good for coordinating which scene is currently being displayed to the user, which makes it easy to understand from an outside coder's perspective, as opposed to having each individual script change the scene when an event is triggered. The game was first outlined in my design document, alongside a couple of diagrams that we used to illustrate the basic behavior of the finite state machine of the enemy, as well as the general flow of the game. This served as the groundwork for everything from the beginning, including the code and the art. From my research, having a robust plan going into a project is incredibly important in the creation, especially within game development where overscoping can often be a pretty consequential issue. This especially applies to me as a solo developer working within a limited time frame. This experience is pretty professionally relevant, as any professional will have due dates and deadlines that they need to adhere to. The first prototypes of the raycasting mechanics were created in a separate Unity project, which was completed as a side project based on the raycasting workshop that we did in class in order to make it applicable in 2D. These allow me to refine those mechanics in a sandbox environment without having to worry about the other game systems that may conflict with it. The same goes for the finite state machine of the enemy. This was also created as part of a workshop, but not fully finished. The transition between states was not polished and didn't really work as well as it should have done. However, the basics of this program, such as the master class and the abstract class, were used as the basic for the enemy behavior in GOLDRUSH. This was professionally relevant since one of the biggest parts of code is being prototyped separately, which allows simplified debugging and a more streamlined workflow. The actual game was written entirely in C# by me. C# is a pretty professionally relevant language as it's used a lot within the Unity engine, which, as mentioned earlier, is a pretty popular gaming engine in terms of the AAA development. All the code is original, although I did use a couple of tutorials on YouTube to deepen my understanding of certain subjects. Although it is worth noting, none of the code was lifted directly from videos. I used an object-oriented approach to programming within the game, which is a programming paradigm that is based on the concept of objects, which contain data and code that's used to manipulate said data. In OOP, objects are defined as classes, which specifies the properties and behaviors that objects of that class will have. This allows for code to be organized into reusable, modular units, making it easier to maintain and extend over time. OOP's encouragement of code reusability can save a lot of time as opposed to functional programming. Speaking of functional programming, I did research the professional suitability of functional versus object-oriented programming and found the latter to be much more widely adopted than the former. It also specifically suits my project a lot more, as I'm instantiating a lot of objects that would need to reuse code due to them being prefabs. Prefabs are also a useful tool in terms of memory management and not spawning as many enemies as you could possibly need and only spawning the required amount, for example, which would be important in the professional context of shipping a game and making sure that memory management was adhered to. Going back to object-oriented programming, this paradigm means I've essentially built the building blocks of a larger project which can be much more easily expanded upon in the future should I decide to take this project forward. Lastly, my research showed that one of the most important elements of professional code is meaningful variable names as well as the commented code. These result in a third party being much more easily able to access your code for your project, as well as, for example, coming back to a project after a certain amount of time when you no longer remember what X and Y might mean. By calling my variables names in which they are non-ambiguous and instantly recognizable, I greatly improve the chances that a development could be opened up to a team, or I could take on again in the future when I have more experience. Examples of my code are being shown on screen now, so if you want to read through any part of the code specifically, feel free to pause and read through. Hopefully you'll be able to decipher what any given function does just by the variable names, or failing that, comments left within the code. I found myself to be very engaged within this module, attending every in-person workshop and working on this project by myself from about week 4, or at least the prototypes. I completed every workshop except the final 2 due to me spending that time to develop the game in my lecture so that I could have the input of the lecturers and my fellow students. Overall, I'd estimate I'd spent about 50 hours on the final project and the tangential research related to it. Outside of that, I've spent a decent amount of time helping other students with their work, which is a very effective way of consolidating my knowledge as well as helping them gain it. Lastly, I've been very active within the module Discord, keeping up with the current discussion and trying to learn from others' mistakes. As an overall reflection on my project, I'd say I'm very happy with the end result, having almost every feature that I originally planned for in my design document included. Although there are certainly areas for development, namely in the finite state machine and a lot of syntax and optimization, small bits and pieces, I would say that I greatly improved my knowledge and ability to code with the creation of GOLDRUSH in relation to almost all aspects, with a very important one being source control, which was something I had very little experience of going in, which should be a lot of use to me professionally.